Hello everybody, this is Avantik here. Today we'll be discussing about decision trees. The agenda for today's discussion is, introduction to decision trees, decision tree algorithm, understanding what happens mathematically in it, understanding, how decision trees can be used for classification, decision tree can be used for regression, advantages and limitations of decision trees. Let's first get started with introduction to decision trees. Okay. It's a non-parametric supervised learning method for regression and classification. In simple words, what it means is you do not need to configure a lot to create decision trees. Okay, the algorithm interprets some of its configurable parameters from the data itself. That is what is non-parametric. Okay, so non-parametric algorithms generalize as well. Okay, it gets information about the data and its hyperparameters, whatever they are, is less sensitive. Okay, and it can be used for regression and classification, though decision trees were initially meant for classification, but later on due to some advancements that happened, it can be used for regression as well, but it's most popular for classification. It's very similar to playing dumb charts. Okay, so what is this game, right? So there are two teams. One person is given a name of a movie from another team, from the other team. Okay, he has to enact, and his team or her team has to ask the right set of questions to predict the movie. Okay, so how is a good dumb charts player different from a not so good dumb chart player? Is that a good player will ask lesser questions. Okay, and with lesser question means lesser computation, he's able to get the movie right. Okay, compared to the other guy, the other non-so-efficient guy. Here the questions are actually framed into a tree, and each node is a question. Okay, let me show it how it looks like. Say you have this data. Okay, this is a tennis data. Outlook, temperature, humidity, wind, these are like weather factors, and the target column is play or not play. Okay, so based on these parameters, you should train your model so that at the end of it, given this 4 parameter, you can predict if the play will happen or not. Okay, and the decision tree classifier, since this is a classification, the target is discrete in nature, decision tree classifier will actually generate a tree something like this. Okay, so this is the optimized tree that you can see here. So the first question is about outlook. Is the outlook sunny, overcast, or rain? If it is overcast, okay, so he'll always play. That's what it means. Okay, the prediction is play. If it is humidity and overcast, outlook is sunny and humidity is normal, he or she will play. Okay, that's the prediction. So given a tree, this is how you predict. Okay, of course, now let's understand the algorithm. Okay, what happens internally to generate this tree. Okay, let's understand how decision tree algorithm works. It is based on CART, okay, and which is an advanced round of ID3 algorithm invented by Ross Quinlan in 1986. Okay, and this ID3 is the one that we'll try to understand, and CART and the other advancements are based on it. Okay, the assumption of ID3 is the columns are categorical. That means the feature data is categorical. Also, the target is categorical. So that's the fundamental assumption of ID3. With time, we got another modification or advancement on that, C4.5, which is based on ID3, and it converts the continuous features into category. The feature data can now be continuous with this advancement, C4.5. Okay, target is still categorical. And a later advancement came, that is CART, which is based on C4.5, where target also can be continuous. Okay, scikit-learn is decision tree implementation of scikit-learn is based on CART. Okay, and here the whole point is what is the question to be asked, rather what is the node value, right? In the above case, what should be the order? Like we say this order, we could have started wind, strong, weak, outlook, come here, right? So what should be the questions, what should be the order? So how does decision tree figure that out? It tries to ask a question so that the branches of it are homogeneous. Okay, For example, if this is the question, it expects the data which falls here and all more homogeneous. More homogeneous means less entropy. So that's what we need to understand to get deeper into it. What is entropy? Entropy is randomness in the system. Okay, measure of the randomness in the system. If you have some data and if all the data are of same type, then you can say entropy of this type of data is 0. If there is a data like this and it consists of two classes, 50% of the data is one class and 50% is another class, then you can say entropy of the system is 1. Okay, so that's what we see here. So it is the entropy of the system is 0 if it is class A, or class B. As it reaches equal distribution of both of them, the entropy is at the highest. Okay, to calculate the entropy, this is the probability of yes, Q is the probability of no, given the data consists of only yes or no. So if this is how it boils down to: probability minus of probability of yes into log 2 of probability of yes, minus probability of no into log 2 of probability of no. If there are more classes, you need to continue doing this, right? And for a data set like ours, we are doing this distribution of yes and no. So we can find in our 14 rows data, 9 is yes and 5 is row. So the entropy of this play data set is minus 9 into 14, that is yes dot np 9 into 14, minus 5 into 14 dot np 5 into 14. Okay, so the entropy of this data set is 0.94. Okay, so this is the measure of the randomness of the data. 1 means highest, 0 is the lowest. Okay, now the next important thing that we need to understand is information gain. Okay, so as far as information gain is concerned, it should be highest. Okay, so your splitting decision should create the highest, should return the highest information gain. That's the whole point. Okay, information gain is equal to entropy minus, okay, for all the attribute, okay, sigma or sum of all the attribute, probability of a particular attribute into entropy of that particular attribute. We'll understand it as we start calculating throughout. Okay, we intend to choose the attribute. See, in the above case, it could have chosen outlook, humidity, and wind when it was creating the first node here, but it chose outlook because on splitting based on outlook, the information gain was highest. Okay, so you have to maximize information gain and minimize entropy of the, maximize information gain of this node and minimize entropy of the subsets. That's the whole point. Okay, so let's do the calculations, let's do the math, then we'll understand the entire flow. I'll take you through the entire process. It's be a little patient. It takes some time to do the calculation, but we have taking a simpler data set to understand this whole. Okay, so what do we want to do? We want to understand gain when you are splitting by outlook. We want to understand gain when you are splitting by temperature, humidity, and wind. Okay, and whichever is the highest will split based on that. Okay, as we can see here in our this situation, the information gain for outlook was the highest. Okay, compared to your temperature, humidity, and wind. You can see these are the values: temperature, humidity, wind, and for outlook it was this value, right? So let's learn to calculate, and we know what to do after calculation. We need to compare. Okay, so to calculate the gain on splitting by outlook, what you have to do, this is the entropy of play, which we have already calculated, and for each of the attribute of outlook we need to calculate, do this math, each of the attribute. Okay, so outlook has 3 values: sunny, overcast, and rain. Okay, so probability of sunny, outlook is sunny, entropy when outlook is sunny. So we have to do this for all the 3 data. Let's now try to do this mathematically. Okay, so for sunny data, this was the number of rows which matches sunny here. Okay, and in this data we can see there are 3 no's and 2 yes. Okay, so 3 no's and 2 yes. So for, okay, we need to calculate this value. Let's try to do the math, how to generate this decision tree. Okay, first is gain of when you split it by outlook. So what we have to do, this is the entropy of the entire data set, and we have to calculate entropy. We have to, and this is what gains formula is. We for each attribute, like we have sunny, we have overcast, we have rainy. There are three attributes. So for all these attributes, we have to calculate the probability of that particular event and entropy of play when it is sunny, entropy of play when it is overcast, entropy of play when it is rainy. Okay, so this is what we have to figure out. So first we have to get the data which is sunny. Okay, so that's what we did here. Okay, now for this data set, we need to find entropy of play when the outlook is sunny. So that is what it is. So play is no is 3. Okay, so 3 by 5, np log to 3 by 5, and yes is 2 by 5. So this is the entropy of play when the outlook is sunny. Similarly, we want to calculate entropy of play when outlook is overcast. So you can see here, for outlook is overcast, all play is of same type. There is no entropy. Data is homogeneous. So the entropy is 0. Similarly for rainy, okay. Similarly for rainy, let me do it for rainy. Right. Okay, let's see for rainy. So this is for rainy, and we can see 3 yes and 2 no when it is rainy. So this is what is, and eventually this is the value, right? 2 no, so 2 by 5 dot np log to 2 by 5. Okay, and 3 yes, so 3 by 5. This is the math, and this is the number. So we have calculated entropy of play when it is rainy, entropy of play when it is overcast, entropy of play when it is sunny. Okay, so to find the information gain, okay, when the based on when the splitting is based on the outlook, entropy of play, that is what we have calculated, 5 into 40, 5 divided by 14. This is the sunny entropy of sunny, probability of sunny, and entropy of sunny was the value that we calculated. 4 by 14 is for overcast, right? See here, overcast. And since the entropy is 0, we multiply 0 over here. 5 by 14 and entropy of play out like rain. So if on doing the entire thing, we get the value like this, 0.2467, right? The similar way we'll be calculating for temperature, humidity, and wind, and these are the information gain. As we can see from this diagram, from these values, that information gain on splitting by outlook is most, right? So that is where our decision will be based on this outlook. So this is the tree that is generated now. Okay, and let's see what happens when the for outlook is equal to overcast. The entropy is 0 since all the data is of same cast. So if it is outlook overcast, then the final node is true, right? Then the final node is true. You don't have to do anything over here. Let's see the sunny part. Okay, so in case of sunny, we can see this is the data distribution, 3 no and 2 yes. Let's now divide, let's now branch more sunny out. Okay, so the entropy of the current data set is this, right? Okay, entropy of the current data set 3 by 2 minus 3 by 5 into np 3 by 5 and 2 yes. So this is the value here. Okay, okay, so this is the entropy of the current, the data set which has come to the sunny part. Now you want to calculate, we have a few features here like humidity and windy. What should come here, right? These are the two things we need to compare. Humidity, windy, and temperature, 3 things. Okay, so whichever is the highest information gain will come here, right? So let's see. So when you're dividing by humidity, okay, you can see here humidity high. So there are 2 classes, and for high, it is all no. For normal, it is all yes, right? So this is the entropy for the high attribute, and the normal attribute will be 0. Okay, the entropy for high attribute and the low normal attribute, because all of them is of same class. You don't need to calculate it. We know that, you know, for this feature the entropy is 0, for this feature the entropy is 0. Okay, so that's why 0 0. So finally the information gain for humidity will be this value minus 0. Let's see information gain for windy. Okay, now wind for, let's calculate for wind is equal to false. Okay, for wind is equal to false. We have this value, this value, this value. These three values are there, right? Okay, so how many false are there? False 3, and in 3 false, 1 positive, 2 negative. True. 2 true. One is yes, one is no. So 1 positive, 1 negative. Right? So you can see here, one positive, one negative. That means it is, uh, you know, the entropy of this data will be 1. Okay, this data we have to calculate. Okay, so to calculate entropy of false, like entropy wind false, 1 by 3, total 3 data into log 2 1 by 3, 2 by 3 into log 2 2 by 3. So this is the value, and the entire, uh, okay, the entropy of based on windy will be, this is the entire entropy of this, of the data which is coming to the sunny branch, minus entropy of wind false, and entropy of wind true is 1. Okay, so it boils down to 0.01. Okay, so this is the entropy based on information gain on splitting on windy. This is the information based on splitting on humidity. Let's see what happens in temperature. In case of temperature, for the data which comes here, temperature, you can see here there are 3 classes: hot 2, mild 1, and hot 2, mild 2, and cool 1. Hot 2 means it is always no, right? Hot 2 means it's always no. So the entropy of the data is, right? So hot 2, mild 2, cold, hot, mild, cold. Mild 2, cool is 1, right? Cool is 1. Hot 2. Hot 2, and play no. So it is quite homogeneous. 2 negative, 0 positive, right? So the entropy of this will be the, okay, and mild, there are 2 mild and 1 1 1 1. So it is 1 plus 1 minus, right? And cool, of course, it will be of high entropy cool. Yes. So 1 positive. That's it. 1 positive. Right? So hot, for hot it is highly homogeneous, homogeneous. Okay, so we can see here 2 by 5, entropy is 0. For cool, 1 by 5, right? 5 is the total number of events, 1 by 5. And see here also it is 1 class and no imbalance here. I mean, highly imbalanced here. This is of 1 class and this is of 0. So it is again 1 by 5 and the entropy is 0. And here you see 2 and the entropy is pretty high because both are equally distributed 1:1. So on doing this calculation, we found this 0.57. Okay, so what we can see out here is the entropy for this is 0.57, uh, 0.019, temperature is 0.57, wind is 0.19, and humidity is pretty high, 0.97. So that's the answer. So you can see that's the answer over here. You do the same way for the data which is under rainy. Okay, so here splitting the rainy branch. Okay, so this is the data which is rainy here. So let's calculate entropy of this data. So we can see 3 by 3 and 2. So that is what the math says. So this is the entropy of this data. Now we want to know what happens when we split it based, what is the information gain when we split it by temperature. Okay, so you can see here, so there are two values of temperature. One is mild and cool. For mild, 1, 2, 3. Cool, it is 2. Right, and it is 1 plus, 1 minus, right? Yes, no. And then mild, it is yes, yes. 2 yes, 1 no. 2 plus, 1 minus, right? So that's why the math here comes. Okay, so it is 1 by 3 and 2 by 3 function. Okay, so 1 by 3 and 2 by 3. So if you look in the past, we have calculated this. See, this is 1 by 3 and 2 by 3. It is 0.918. So that's why I'm putting here 0.918 directly, right? 0.918. Okay, so this is for mild part, and this is the entropy for this is, I mean, the probability for this is 3 by 5, right? Okay, there are 3 mild, that's a 3 by 5. Then here 2 by 5 and entropy is 1. So if you do the calculation, okay, it boils down to this 0.02. Then we do this for windy. Okay, and windy, let's calculate the, okay, so windy, false, false, yes, yes, false, yes. So you're playing in all the false cases, and no. So of course the entropy is 0 for both the cases, right? Okay. So that's why for windy it is 0, 0. So the information gain is this, and for humidity you again do the math, again do the same calculation. Information is this. So what we can see here, information gain when you're splitting based on windy is high compared to others, and that's why your tree becomes, this is a final tree. Okay, so you can go through the entire notebook and do the maths by yourself to understand, you know, what's happening. Once you understand this ID3, others are just extrapolation of this. Now we have understood how this maths behind the decision tree. Okay, this is for categorical data. If it is continuous data, that is the implementation using C4.5 and all, there are internal things which you can refer how it converts continuous data into categorical data, and then it does the similar stuff. Okay, but that's the logic all about. Okay, so cart is the one, and one important aspect here is it is kind of assumption in decision trees that feature are independent of each other. Okay, and decision tree classification works, since it is card based, it works on data which is feature data which is continuous. Okay, and different tree will be generated when you have same data. I'll do this classification part one more time. Okay, now that we know the calculation, the entropy, the information gain that happens for calculation of the decision tree. So you might try this using Gini impurity index as well. So just the calculation part is different, and rest of the stuff is almost same. You can try that out. Now we really want to get into decision tree for classification, and rather than getting into mathematical part, we'll use scikit-learn APIs like decision tree classifier and all that to get it done. A few important notes about decision tree for classification is as we saw there, the leaf nodes are decisions. Okay, so and CART is the algorithm which is scikit-learn following to implement its decision tree. If the same tree is same data is given in different order, it will generate different trees. Should try this out. Same data, change the order, you'll see a different decision tree. Let's start with iris data. So this is the data that we are loading, and we can see we have 4 columns over here. Okay, and with the criteria that we are choosing here is entropy, which is, but it is Guinea by default. Guinea is preferred because it does not use logarithm. Taking entropy in this case. No need to cross check which one is better. Both of these almost results in the same tree. Okay, we should not get into a situation where one is superior than other in most of the situation. Works well. Then you need to divide the data into train and trace so that we can train the model with one part of the data and validate it with another part of the data. Okay, this is the training part where you're passing train X and train Y. Since the data is the feature data is continuous, the targets data is categorical. Okay, so this continuous data will be taken care internally and converted into categorical. It will be all taken care. You don't have to deal anything in there. Okay, and the tree that is generated here, you can actually dump the tree. Okay, and see that. So this is the web page. Okay, so I can open it. Okay, so this is the web page. So when you do this export graph is dt.tree, it generates a file. Okay, something like this. Okay, this is not the same file, but it generates a file. You need to copy this, Control C, and paste it over here. Okay, generate graph. It will generate the tree here. This is not the same tree. Okay, but this is how you generate it. So this is the tree, and here you can see X3 is the last feature. This is the second last feature. So you can see this is the tree that is generated, and the leaf node will have entropy of 0, right? Entropy of 0. It tries to minimize this entropy, right? In this case, we are not giving any limit to the height of the tree. So remember, if you keep adding more and more data to the decision tree, the height will keep on increasing. That is what is overfitting, right? We'll see that later. Since we are not doing that, it tries to generate the tree, and this is what it is. So you can see the entropy. The leaf nodes has entropy is equal to 0. Okay, and for doing the prediction, pass the tree and it will predict which class the data belongs to. Okay, and decision trees algorithm works pretty well because important features will definitely go up the tree. So decision trees are a good way to understand feature importances as well. If you do dt.feature importances, it will tell you this is the importance of the first feature, second feature, third feature, and fourth feature. You can see third and fourth feature seems to be highly important. Okay, let's now understand how this decision tree works without the generated data. This is a pretty interesting example. Okay, so you are generating data like this. So you are using make blobs, and this is one data, this is another, this is another. Okay, these are different classes of data. Okay, 4 class data. Now we are using decision tree and training the model. Okay, so basically, this is what it needs to separate. So now let's see. How does it do that? So here in this step, we are generating all the data throughout so that we can see the decision boundary. So this is a very popular code in understanding these things. So what am I doing here? From least value of mean to max value of each thing, I'm generating all the data here, mesh grid. Okay, and then I am predicting it after combining all the results here. Okay, and this is what the prediction looks like. You can see here, this is one decision, this is another, right? So you can see here, this decision tree separation will always be in edges, right? In edges like this. Okay, so this is how a decision tree separate. You can add more and more classes. You can add some class over here. You can see, continue seeing it in a complex shape, right? Try this code out. Let's understand now decision tree for regression. Okay, so fundamentally, ID3 was not designed to have decision tree for regression. Okay, it was a later modification using CART, which was capable of doing this. That is modification over information gain was based on categorical data only, right? So now the error, what you have to minimize is mean squared error. Okay, so let's understand the data again with tennis data. And okay, so it tries to minimize the mean squared error. Okay, so this is your feature data, and the target is continuous here. The time that which will play tennis, the minutes, I guess. Or okay, this is what it is, and this is the for weather factors. Yeah. So since these are categorical values, and we need to fit this to decision tree, we need to convert them into labels, right? Okay, so that's what we are doing here. We are converting this categorical values into labels. Okay, only these four columns, not the last one. We are converting this into labels. Then we are passing this to decision tree, except for the time column. We are passing all of them, and it generates the tree. Now we want to see the tree generated. So to generate the tree with the same column names, we can pass the feature names over here: outlook, temperature, humidity, and windy. So this is the tree it generates for this particular data set, right? So let's say we have to predict for after playtime. Okay, so let me generate the data. So after doing the transformation, this is how the tree data looks like. So for example, I have to predict for 2111. Okay, so that's what we have to predict. So how does this thing work? 2 less than false. The false, it goes here, right? False. This is 1, right? Less than equal to 1. So this is true. So the value will be 23. Right, value will be 23. Here also, similar to earlier case, you can calculate feature importances. We can see here, these two features are very important, and of course all of them are important in this case. Okay. So let's now understand what are the advantages and limitations of decision tree. It's highly interpretable, since it is just and visualized, and can be very easily visualized. A tree like that gives a clear picture what is important, what and how does the entire thing flows. Okay, it can deal with missing data, no problem with decision tree. It handles it well. You don't have to do any pre-processing for that. No need to normalize the data. No need to have one code encoding in case of nominal values, right? Your label encoding will work. Okay, and it handles numerical and categorical values. You don't have to do anything with that. It supports multi-output. Now let's understand what is multi-output. Okay, you might have seen this in case of a linear regression. In case of nearest neighbors, your target can be more than one columns. That target can be 2D. Okay, as long as the targets are not dependent on each other, there is no interdependency or there is no correlation between the target, you can predict them with different models as well. For n targets, you need n models there. Okay, which is where different computation, but more or less the target will be dependent on each other, right? The feature targets will be related to each other. So that is where your you can use one model, and based on that you can predict multiple targets. So decision tree supports multiple targets here. Now let's talk about decision limitations of decision tree. Even as you keep increasing the data, and if you're not controlling the height or the number of leaves in the last node, you have a potential tendency to overfit. Okay, so the number of questions can keep on increasing and increasing. So decision tree is prone to overfit. Okay, a slight change in the order of data can create a overall different decision tree. Okay, imbalanced data sets needs to be will generate bias tree. So you need to balance one before feeding it to the data. So ensemble is another technique which will handle the first two situations. Okay, and fundamentally decision tree has a concept of pruning. Like you generate the tree, then you chop off some part from the bottom of. There are two types of pruning. One is pre-pruning and post-pruning. Pre-pruning means you typically are configuring this is the height of the tree that I want, and you generate tree based on that. Post-pruning means you generate the tree and chop off some parts from the tree. That is what post-pruning is. Okay. Pruning is unfortunately not available directly in scikit, but you can achieve the same thing using, you can configure mean sample sleeve, that number of leaf, minimum number of leaf at each node, last node you want to have, and the max height. Using this, you almost achieve the same concept as pruning. That's all from decision trees. Thank you guys. See you in the next video.